Good afternoon and a very warm welcome to Isifundi Training on this, our third of our April Bite-Sized Corrosion series, where we're taking an in-depth look at corrosion failures. Of course, when there's a failure, our primary aim is often to get operations back up and running as quickly as possible. But in our discussion with Neil Webb, we learned that it's really important that we try to do everything in our power not to disturb the evidence, if at all possible, because the evidence helps us answer the questions of why and how did it fail. And it was also interesting in our discussion with Rolf Mostert to discover that some corrosion failures can actually be discovered during routine testing. And then in some instances, planned maintenance can be scheduled to prevent the actual corrosion failure from being catastrophic. Now, today's conversation, I'm really confident you're going to discover more valuable insights as we open our discussion with Melanie Smit from Mintek. What I love about Melanie is her passion about exploring failures and her desire to share her findings, and I have no doubt we're going to enjoy today's discussion. So welcome, Melanie. Thank you so much for joining us today. Now, as we get started, I know that you find it helpful to look at failure analysis in the greater scheme of corrosion science. Would you take us through your thoughts?
Hi, Vanessa. Yeah, from my experience with corrosion science, there's quite a few legs to it. We look at corrosion testing to standards or material selection and evaluation, corrosion monitoring, research, various testing like electrochemical corrosion testing, and then what we're discussing today, failure analysis.
Okay, and where do you fit in this whole scheme of things? Do you do all facets of that?
Well, most of them or some of it to some degree. We're looking at materials information and advice at Mintek. So we have access to a lot of information, old literature or new literature, current literature, and we can advise and assist with current projects. We also do quite a bit of corrosion testing. So our biggest focus is on extreme environments. So we have high temperature corrosion tests. We have, like I mentioned, the electrochemical corrosion tests. So all of these help us to assess corrosion and materials performance to corrosion, and then help us to select a correct material for a specific environment. A lot of our clients are in the high temperature and petrochemical industries, so it's very critical for them to know what materials to use to manufacture parts out of.
You also obviously do failure analyses.
Yes, that's one of our key aspects, is that we do want to see the failure, or if there has been a failure. A lot of the test work is to try, like Rolf mentioned last week, to prevent failures. But yeah, one of our key aspects is to perform failure investigations, where we would look at the material as a whole. We look at its performance from a metallurgical perspective, so the microstructure, as well as the chemical nature of the environment and some mechanical properties.
Now, Melanie, with your experience, what would you say is one of the forms of corrosion which perhaps people find unexpected or seriously unanticipated?
One of the most common type of failure that we do get is under deposit corrosion. When you're working in, for example, in a hydrometallurgical field, I actually had a corrosion failure on a reactor where settled deposits were actually causing the corrosion. Although the tank was being stirred, it wasn't adequately stirred.
Okay, so you were getting a settling out,
Yes.
And then underneath that you get corrosion.
It took us quite a bit of time to figure out that it was actually under deposit corrosion, because the samples we removed, this is of the corrosion attack, and you can see there's not much deposit on the sample that we received from the customer. So we did an investigation. I think the next image shows cross-section through that pitting corrosion, where we can see massive subsurface corrosion or attack into the steel, resulting in leaking. From this investigation, like I mentioned before, it was a BIOX reactor, so it was a very corrosive environment. And we looked at it, we couldn't understand why it was pitting. So we looked at the weld was fine. But in the end of the day, we tried to do a simulated corrosion test. And I think the next slide is quite a fun one.
That looks like a great
Running a
scenario.
couple of vessels with a few alloys to try and see if we could simulate or predict the corrosion. And here we actually saw that we had a lot of settling onto the samples, although we were stirring as well from underneath. So the deposits just had a natural nature to settle. And this is what led us to the conclusion that it was under deposit corrosion. From these corrosion tests, we actually looked at various other alloys. The vessel was actually made of, I think it was 3 or 4 stainless steel. So these are the coupons that we exposed in those vessels, and we could see the pitting corrosion at the top of the coupon and on the sides. And then one of the additional alloys that we looked at to try and up alloy is the 2205, which showed quite a bit of resistance to this type of attack. And that's what we went with in the end of the day. I think the biggest solution to this problem was also to change the design of the vessel, because there were areas where we had deposits still depositing in the tank, and the stirring wasn't adequate. So a lot of changes were made from that aspect, which then resolved the issue.
That's so interesting, because I think it ties back with what Neil was saying in our first session. Sometimes you get submitted a sample during a failure analysis and you can't really fully grapple with what the situation is, again, because the evidence had been disturbed. So you never saw the deposit.
Yeah.
So it was difficult to say this is an under deposit challenge.
Yes.
That is very, very interesting, and looks like you have quite a lot of fun with small samples of steel and bubbling them away and what looks like a fine witch's brew. Melanie, I know that, just moving on, you mentioned that there was pitting in this, and that is a form of corrosion that we all hear about. Instinctively, we get the idea that, pitting isn't a good idea. Is pitting a form of corrosion that you see a lot?
Yes, Vanessa, we do see a lot of pitting corrosion, especially with alloys that form a passive film for protection. For example, stainless steels, aluminium alloys, titanium. So because stainless steel has this protective film, any defect or damage to this layer can initiate a pitting corrosion, because stainless steel react differently in the environment. So specific environments are also something to look at. With stainless steel specifically, chloride environments are quite a concern. I think everybody knows about this. Well, the biggest challenge with pitting corrosion is to actually identify them and find them. We received probably 9 duplex stainless steel pipes, and we were struggling to find the pits because they were so small. So in this image, you can see the skull bar is 1 millimeter at the top right of the
tiny
image. And then you can see the small corrosion pit on the surface of the tubes or pipes. There is some discoloration around the pinholes, which also just shows the active nature of the pitting, and then also the change in the passive film. So the discoloration, when you're welding, you have those tint lines. So a similar thing happens with corrosion. You have your passive film is changing, so it leads to discoloration. This one was quite, the pits were so small, but if we go to the next picture I sent you, you could actually see how catastrophic the pitting was. So from the pinhole at the top, we had excessive damage and corrosion of the material underneath, which was quite extreme.
That is absolutely terrifying, actually, that really what's on the surface belies what is happening underneath. I've tended to disregard the pitting. There's just a few holes, but changing my mind a little bit.
To solve problems with pitting is quite difficult. So you need to change the environment. Often you cannot, because you're dealing with chloride containing water for specific things. We don't add chloride to everything necessarily. We add it because we have to. So one would have to go for a more resistant material, maybe a coating. I don't have a lot of knowledge on coatings, but in metallurgy, with the hydrometallurgical field, we do have very special alloys that we can look at for various environments, and then also to improve your design to try and prevent pitting. So you would, in a stainless steel case, and most alloys, if you do weld, you'll passivate a pickle. So it all comes with fabrication, your design to prevent low flow areas where you have chloride that could build up or something like that.
That is interesting. It's very easy to be flippant and say, well, just change the environment or change the steel. The reality is that very often that can't be done. And so when it's nice to hear that there are some fabrication changes that can be made. And I do think we don't necessarily always look at the coatings or the protective layers that we could add to the materials that might withstand the environment. So I think you're right. I think there is some synergy there that we could explore a bit further. Right. Now, Melanie, you sent me a photograph of a burst pipe, which I thought was just a burst pipe. But you told me that this picture actually tells us a bit more than just a burst pipe. Take us through some of what is happening here and how it's happening.
It appears like a burst pipe, and it probably is. It's actually a pipe from a boiler. So boilers basically work at high temperature. We're looking at 300 degrees Celsius.
Okay.
Most of these tubes are made of carbon steel. They've got good strength, and we do quite a lot of investigations on boiler failures. Now, for the ones that don't know what a boiler is, it's basically your fuel gas would run either on the inside or the outside of the tube, and then you have cooling water to try and cool down the hot fuel gases so that they can go through the system. So it's basically a large cooling system, often around a furnace. So it's basically there to cool the furnace. In this specific case, we had quite a lot of oxidation on the tubes, which resulted in this fish mouth fracture or rupture. And we see them quite a lot. So I think there's a next slide where you can, at the bottom of the screen, you can actually see the bulge. And that's why we call it a rupture. It's got that open sort of
looks like fish mouth.
Look to it, yes. Now, on the outside, you can see there's quite a bit of scale, this gold-colored stuff, which was flaked off. And then on the inside, we can see a lot of scale there. This is when we opened up the tube. So a lot of this oxide scale broke off, and it's quite
brittle.
Yes. So from this investigation, we saw that a lot of the deposits built up on the inside of the tube, causing increased temperatures. So we would say hotspots. And that's where, again, we have a deposit build-up, and that then influences the efficiency of your boiler. So the guys would run it higher, if that makes sense. And this just feeds the problem. So we had hotspots, which caused this fish mouth forming. When you look at the metallurgy of this, now carbon steel is usually made of ferrite pearlite microstructure. And here, when we did a cross-section, we could see that a lot of the pearlite had spheroidized. Normally they are laminar, and here we can see that they are nodular. So we could see that damage within the metallurgy of the steel. So we knew that the tube had run hot. We had this excessive deposit. What a lot of people do, it's not something you can always prevent. So we know that the damage does occur. It's a manner of monitoring the boilers during service. And I think for the larger companies, petrochemical, power and all those sort of industries, it's to monitor the boiler tubes. So often we get sets of boiler tubes where we would evaluate the deposits on the inside and on the outside of the tube to assess if there's any damage and then report on that. So it's more prevention or monitoring of the oxidation. And then within time, we could see if there's a buildup, if the boiler needs to be chemically cleaned. So we would also do these sort of tests before and after cleaning, which is very important for boiler health. You know, there's quite a few training sessions on this with some of the petrochemical companies and also water treatment companies. But yeah, this sort of rupture can be quite damaging because, you know, you have to shut down your boiler. So we all know about that with load shedding. If the power station's boilers don't run, we don't have power. So
we now all have a picture in our minds of what is happening at the power stations when there's a shutdown. That is interesting that with ongoing sort of monitoring, you can determine an optimal kind of cleaning or maintenance cycle to try and prevent this from happening. And also to me that the buildup of the scale indicates that it's been running too high, I suppose, in order to keep operating.
It could be anything in the boiler water as well that could have high silicons or silicates. So to find the origin takes a bit of an investigation. But for them, I think they know what the problems are and then they manage it. To up-alloy this could open a whole new book on new types of failures. So if we're looking at, why don't we make them from stainless steel? But then you have risks of other types of failures like stress corrosion cracking or pitting and things that we can't easily monitor for. So they kind of decided, well, this is, it's the devil, kind of thing. So you can actually monitor and how the material will react. It's your maintenance cost in the end of the day.
That's very interesting to me because I think there is often this sense that the product I'm using has failed, therefore we need the next greatest and latest in the stainless steel family to come on board. And I think that there is a very great risk, which you've alluded to, that you don't know how it's going to perform under the operating conditions. And to be fair, I'm not sure that we can model them adequately to really anticipate all the problems, but you might feel differently in that regard.
For me, any sort of environment, we do have graphs and tables and curves and things that we can make estimates on from literature or from research, but a lot of it's in pure solutions or specific environments. And you might have a solution that has a little bit of potassium in, and the potassium could be reacting with something else and changing it. It does become more aggressive, or it has chloride in, for instance, and the chloride levels build up and you're not monitoring it. So, from that aspect, your environment, you are often controlling or trying to control it, but there are instances where you cannot actually monitor or control these. So you have to try and look at that and kind of design those sort of issues out of your system.
I think sometimes there's also the secret ingredient that very often a client omits to disclose during the testing, which could in fact cause the failure completely unwittingly, because if you'd known that that particular component was present, you would never have recommended whichever steel you ended up recommending.
Yeah, we were actually many years ago, many years ago, I think John McKeown was still working with me, or I was still working with him, and we were doing corrosion tests, mass loss tests, as in the example I showed previously, and we were using the plant solutions. Our reactive vessels are made from glass, so the client neglected to let us know that there's fluoride in their solution. So we just saw our glass were being eaten out. So we're like, I think we know what's causing your corrosion. So in the end of the day, yeah. So sometimes we do have those issues.
I think there's much value to be gained from doing a little bit more of the testing. And I know our audience is largely in the engineering fraternity. And just to encourage you, if you're looking at something new or a slightly different scenario, that testing your materials of construction within some of the parameters under which they'll be operating is probably very wise to take into account possible forms of corrosion to prevent this kind of failure. The pitting is reasonably well known, but sometimes you can end up with your underfilmed deposits. And even in the boiler example, that is another form of underfilmed deposit, which I didn't even think of that as being actually part of the corrosion mechanism. It's interesting to me that it tends to be called creep failure.
Yeah.
Is there a reason for the name and where that fits in?
I couldn't tell you. I think Rolf is probably the guy to go into the whole mechanism of the corrosion. But yeah, so you do have microstructural changes in your material. So it's referred to as creep or stress rupture.
Right.
So,
okay. Stress rupture, I can understand. The word creep, I sort of had this little creepy crawly thing in my head, which didn't really work very well. The other thing that I'm finding quite interesting is that under the operating conditions, you're actually getting such a change in the structure of the microstructure of your steel. And I'm wondering whether that happens anywhere under operation, or does the steel look like the sort of typical micrograph? Should it look like that irrespective of the operating conditions, or is there always change into that sort of spherical nodule at higher temperatures?
Actually, you make a good point there, Vanessa, because with these high temperature ruptures or failures, the spheroidization actually changes. So the lamina is what gives steel its strength. And because it's spheroidizing, so you're losing strength in your steel.
Okay.
And that's what in the end causes the rupture is, so your section thickness is designed to handle a certain pressure. And when you start spheroidizing, or when the material starts spheroidizing, it becomes softer. So then it fish melts, its bubbles, like you see in the image, due to hotspots or higher temperatures. And that's because the scale forms like a blanket. So it just gets warmer and warmer and warmer on the tube surface. And that's when it has that plastic deformation. And then when the material that has spheroidized or softened ruptures because it cannot hold the strength that the boiler was designed for or the tubes were designed for. So that's when the rupture occurs.
That's so interesting, literally when a burst is not just a burst. Melanie, our time has flown. This has been a fascinating discussion. There's so much more I'd like to chat with you about. Would you be willing to come back and join us again tomorrow to carry on our conversation?
I'd love to, Vanessa. Thank you.
Thank you. That's wonderful. So thank you for joining us, and I do look forward to seeing you all again tomorrow. Thank you and good afternoon.